Good morning, good afternoon, good evening, and welcome to AI for Good. My name is Bastian Quast of the ITU, the International Telecommunication Union, and it's my privilege to introduce today's webinar. As part of the Climate Science and AI series, Suman Ravuri of DeepMind, and today's session will be hosted by Duncan Watson-Perils. With that, it's now time for me to hand over to our host. So Duncan, over to you.
Thank you very much, Bastian. Absolutely. So I'm delighted to introduce Suman Ravuri, a research scientist at DeepMind, who will discuss the perils and promise of purely data-driven approaches to weather prediction. So I'm really looking forward to this talk. Over to you, Suman. So please feel free to share your screen when you're ready.
Yeah, thank you for that introduction, and then thank you for, I guess, coming today and then listening to this talk. Today I'll be talking about purely data-driven approaches to weather prediction, both sort of the promise and the perils. So I am a research scientist at DeepMind. My background is in machine learning, and maybe compared to some of the people, perhaps most of the people in the audience, I have less of a, I guess, developed background in environmental science, but I'll be talking about a collaborative work that we've been doing with some of my colleagues at DeepMind and the Met Office Informatics Lab. And I wanted to kind of have this pitch for collaboration. I know this part of the speaker series here is to connect people with perhaps my background, so machine learning or artificial intelligence research, but may not have the domain expertise to help solve these global challenges with people who do this type of research day in and day out, but may be fairly new in machine learning. So I found that the collaboration with the Met Office was hugely important to us. And I think this is a great, I guess, venue for which we can have these type of conversations and maybe push forward in terms of new types of techniques that can help solve these big global challenges. So we at DeepMind have been working with the informatics lab for roughly about 3 years. And I think the collaboration was rather nice because we had a complementary skill set. So the Met Office obviously needs no introduction in terms of their domain expertise, environmental science and atmospheric science. And then we at DeepMind focus a lot on core machine learning and AI research. And it's been a wonderful learning experience. Just personally, it kind of felt like being in grad school and learning about new things. So even on a personal note, it was a really interesting, just a really interesting collaboration. And so this will culminated in a paper that came out last year about precipitation nowcasting. So I will discuss this and use this as sort of a case study of some of the highlights we saw in using going with a purely data-driven approach, and maybe some perils and some things that might need a little more looking at to make sure that the models that we develop, maybe using some of these techniques, especially I guess like deep learning type techniques, making sure that these things are useful and not just ones that might look good in a research paper, but not necessarily be useful going forward. This is a bit of background. Here's the outline of the talk. So I'll give sort of the problem statement and data. I have some discussion about baseline models, both physics inspired and ones that are more purely data driven, and discuss maybe some minor issues that needed to be, I guess, put into the fore, and then discuss why we need generative models before section 4, discussing our deep generative model for radar. I will then talk about quantitative verification, which is something this community does quite well, but some of the limitations that we found when we're using very standard metrics to measure, I guess, statistical systems before diving into an expert evaluation and conclusion. This might be old hat for everyone on the call, but just to set the stage, precipitation nowcasting is a high resolution. So think each sort of pixel or grid cell is 1 kilometer by 1 kilometer. Rainfall estimates of, I guess, rainfall or other precipitation in the short term, so sub 2 hours. So why is this important? It's used by expert meteorologists, especially at the Met Office, to do things like issue flood warnings, help identify things around air traffic control, and then provide sort of marine services. And from a machine learning perspective, it also highlights some interesting statistical questions and maybe some interesting questions that we don't necessarily think about that closely, and maybe that we should more. So making sure that we have predictions across multiple spatial and temporal scales that are consistent while accounting for uncertainty in a proper way are really, really important. And I think one that is very important and probably has, that is something, I guess, less considered in the ML community is being able to capture rare events. So the rare events are these type of events that are both sort of rare and important, such as flooding events that typically maybe a traditional system might not be able to find. And in Nowcasting itself, this is, sort of a regime in which NWPs, or numerical weather prediction systems, these big weather and climate simulation systems, perform poorly. So this is an area in which data-driven approaches should be pretty good relative to the baseline. So even in kind of this very controlled setting, I think it is a really interesting case study. And then the data that we use are this really nice radar data set in the UK that we got from the Met Office. It comes every 5 minutes, so roughly 300 times a day. And the radar field is pretty big if you're coming from computer vision. So 1,500 pixels by 1,300 pixels, as mentioned before, each pixel or like grid cell is 1 kilometer by 1 kilometer. And we have data from like 2016 onward. And one thing that I would like to note, especially coming from an ML background, is that even from a data standpoint, this is much bigger than maybe the data sets that we would be used to. So in the bottom left-hand corner, there's this sample from MNIST, and this is a 28 pixel by 28 pixel black and white images of digits. And a standard large-scale data set is ImageNet, so this picture of the dog that's on the top left, and that's 128 by 128 or 256 by 256. And so already you can see from an engineering perspective, this is much, much bigger than the types of things that we are generally used to. We also have some work on the US using the MRMS, or multi-resolution, multi-scale data set from 2017 to 2019. And it has sort of a similar horizontal resolution, and then it has a nominal temporal resolution of about 2 minutes, but actually each of the radar sites updates asynchronously. So there's a volume scan that happens every 5 to 10 minutes. And so if you actually look at consecutive frames in the radar images, you'll see that one radar site will update while the other ones are static, and sort of vice versa. So there's this weird inchworming effect. But I think what we're mostly interested in are kind of like the models and how these things perform. And I think in order to, I guess, like set boundaries and I guess inspire what is going to be said next in the talk is this quote that I think everyone kind of knows, but it's helpful to reiterate, which is, all models are wrong, but some are useful. So this is attributed to the statistician George Box, but there's been historical antecedents, maybe going back a couple centuries beforehand. And George Box was obviously talking about statistical models, but I think this is probably also broadly true of scientific models. And I think this is a good lens through which we can evaluate models that are out there and understand kind of like what are the things that are wrong with them, and then understanding to the extent to which, even if they are wrong, to the extent to which they're useful. So just to kind of kick this off, we'll look at sort of a physics type system. So either looking at Lagrangian persistence or like an ensemble or probabilistic version called pi steps. And the basic idea is you're kind of given a couple radar images of the recent past, so 2 of the recent past, and you'll get an advection field by estimating the optical flow subject to smoothness constraints. And then your prediction is just extrapolating your inputs based on an advection field. So you have very strong inductive biases here, and that's great. And if most of your rain is advective, or that's what you care about, this is a pretty good model. And I think the other nice thing that it's nice is you've made very strong statements about what you consider are desiderata that you care about in your model, and things that you've explicitly not had. So you say things like convective initiation or rain that's coming up de novo is something that you might not bake into your model. Or if you're steps, you might do a perturbation of an advection field and perturbation of precipitation, but you're saying to a first order everything is advection. So what's wrong is a lot of thunderstorm or other type events may not be captured in this model. And obviously, and it also struggles with orography. So if you look at radar over the mountains, these models don't work particularly that well. But having very explicit the things that are wrong in the model is not necessarily that bad. So we're gonna, I guess, sort of as a toy, kind of do a hybrid approach of kind of this physics model and a neural network model and kind of see what happens when you have some extension of this. So we're going to do a data-driven approach of optical flow. Mainly what we had in our lab is an idea that maybe this would be a little bit better with orography because we don't necessarily make strong statements about the smoothness advection fields. And the hope is that this is something that's learned in the model. So this model estimates optical flow by looking at sort of high resolution images. So these boxes here you can kind of think of as the previous two radar frames, and you have a convolutional neural network that generates features from these at different spatial resolutions. So there's the original resolution, downsampled or upscaled by a factor of 2, factor of 4, until you have very small images. And then there is a cost volume layer, which you can think of as cross correlation. And from this cross correlation, you first calculate an optical flow at a coarse resolution, advect the low resolution feature toward the high resolution feature, and then do this process at the next highest layer, and then do iterative refinement of the optical flow estimation. So one thing that's interesting to notice that is even with the strong inductive bias that we have in the model, we see that there is some advection, but we also have this smearing effect. And part of this we'll get into is a particular reason for this. And another interesting thing that I want to seed with the audience is that this model, even though it doesn't give you physically consistent predictions, actually scores quite well in terms of metrics, which may or may not be problematic in terms of what your downstream task is. But to our first order, even though we have this hybrid system, it has this smearing effect that we don't necessarily want. But why don't we, say that maybe some of the issue is the inductive bias itself, and why don't we go for, I think, a purely data-driven approach. And so here's a really nice neural network architecture called a UNet, which was first proposed for medical image segmentation. And there's been some recent work, both in 2019 and 2020, and stuff that we'd also done internally in terms of using this for precipitation prediction. And has some really nice properties in the architecture, which seem to be pretty good would seem to be, I guess, a nice fit for this particular work. So this UNet architecture, for those that have not noticed or have not used this before, is you're given sort of 4 frames of input, and that's given here. And then there's 3 convolutional layers that happen that occur sort of at the same resolution. And then we downsample this by a factor of 2 while increasing the number of channels, have more convolutional layers, and do this about 1, 2, 3, 4, 5 times. And then we do upsampling at each individual level, and then have this output prediction of what happened over the next 90 minutes. And what makes it UNet nice is the information that it gets comes from sort of the previous resolution coarser image, but also one that happens earlier in the architecture. And so we have this nice accounting for multiple spatial scales here, and we're just using a purely data-driven approach of either using a regression output or a classification output. So this architecture is really, really nice. And you can just throw a large corpus at it and see what happens. There's also a similar model that has been done by some colleagues at Google. So this is an axial attention, or depending on the specifics, the MetNet paper. And this uses a different architecture, but sort of similarly, I think, pretty well inspired, using a convolutional LSTM, which is a temporal encoder over time, and then uses attention to be able to use large context to make predictions at each point of the output, but uses the same classification loss as the UNet. So this is to kind of say these two approaches are very data-driven. The architectures are a little bit different, but they do, I think, pretty smart things. But let's see what the prediction looks like. And one thing that you can see with the prediction is that in the beginning, you'll have some small scale structure, but it gets increasingly blurrier over time. And this is not just these two architectures. This one is for the U-net regression, and you can see similar things for axial tension, but this has been known in the literature. And what is also interesting about this is that this will produce pretty good metrics, and we'll get into that later, but it produces these blurred predictions, which feel like hedging, or maybe something not as high resolution as we want it to be. So, why is this happening? So what's wrong with these models? So one thing that we should do is analyze what we made the implicit probabilistic model here. And what I'm going to say is all of these models are, some probabilistic model with some parameters theta of x of t, and x of t is your prediction radar. So think of the entire trajectory of your predictions from, like, we'll say this is 30, 60, and 90 minutes. And then x less than t is kind of your input to the model. And then h is your height, and then w is your width, and t is sort of time. So for a regression model, say we use mean squared error, you can think of this as sort of linear regression on a pixel-wise level. And you can think of this as like a Gaussian distribution at your label at a particular pixel at time, height, and width, given your input prediction, with your mean of your input prediction and standard deviation here. And I think what's interesting is that you see that your probabilistic model decomposes into conditioned on the past, a product of marginals of your output. And you see something similar in the classification scheme. So your output might be binned to certain prediction values. So say one bin is between 0 millimeters per hour and 0.2 millimeters per hour. Your another bin is between 0.2 and 0.5, et cetera, et cetera. You can see the same decomposition here. And this is a simplification that allows for, I guess, a point-wise accuracy, but it also introduces what, I guess, from a machine learning standpoint, is a conditional independence assumption. And we should really take a look at this conditional independence assumption and see if this is something that's wrong, that we are okay with, or something that we would like to fix. And this might be old hat for people, especially for people with background in graphical models. If not, I'll give sort of a primer to this. But I think it is worth kind of thinking about. So a graphical model is basically a way of identifying, I guess, through, like a graph, of identifying what the independence assumptions are in the model. And here's the conditional independence assumption with kind of the first generation of data-driven approaches, is that given the input, given our past, and we have some prediction of the future, it says that all the information that I need to make my prediction is encoded in the past. And nothing about information about prediction in the future will allow me to make better predictions in different areas. So let me, I guess, make a specific example of this. Say we played a game, and I gave you an input of what happened in the last 20 minutes of the precipitation. And what I want you to do is give me a probabilistic estimate of rain and this pixel, which is blown up for visualization purposes, of this orange dot here. And I tell you, well, I can also give you information of what happened in this green dot here. Would you want this information in order for you to make a better prediction? If your answer is no, and you say all the information I need is in the past, then you are asserting one, I guess, downstream effect of the conditional independence assumption, is that knowing about the green dot will not make you have any better prediction. But if you don't believe that to be true, and you say, well, this green dot will help me make a neighboring prediction, or if another dot that's sort of close to here will make me have a better sense of what happened in the rain in this area, then maybe that this conditional independence assumption may not be true. And I guess sort of belabor the point, but I want to, I guess, sort of show this in sort of two examples. One, which is not a weather example, but one which is a crude and toy analogy to language modeling. So for those that aren't necessarily familiar, language modeling is basically a version of like a completion of a sentence. So given some words of input, this input might be given to some model. What I want the model to give you is a completion of perhaps a sentence, or just a continuation of it. And one thing one of my colleagues did was take, I think, a sentence from, I think, an early version of the paper, and then put this into a language model that came out a few weeks ago that one of some colleagues of ours at DeepMind had. And the way this model works is that it's given all of these words as input, and then it predicts the next word. So we can go through an example here. So precipitation nowcasting, the high resolution forecasting of precipitation up to 2 hours ahead supports the, and then the model spits out 3 different samples. So the first one says supports the decision making process. And then we can do a second sample. So the input again is what's here in black. And then the second sample could be increasingly important issue of flood. And then we might have a third sample that gives supports the effective planning of emergency response. And what I would like to note is that when we make predictions of the future, I really want to know what the information I've also predicted in sort of the near past was. So if I only wanted to know the 4th word, I would really want to know what happened in the 3 words before it, in addition to the words that I was given it as input. If I didn't do that, and I say these things are independent, then I could just pick any words that seem probable given only the past, but now I don't have things that are grammatically correct. So it supports the increasingly planning processes, which doesn't make a ton of sense. So, I mean, this is obviously a cooked up example for language modeling, but why don't we take this back in terms of like weather, a weather experiment. So here is a thought experiment in sort of a one-dimensional case. And so say we have a precipitation front, which is dumping a lot of rain, 30 millimeters per hour, and it's 40 kilometers wide. And it can move in one of 2 directions. So with probability 0.5, it can move 60 kilometers an hour to the west, or with probability 0.5, it can move 60 kilometers an hour to the east. And then 20 kilometers away, there's this city W, city west, which conspicuously looks like London. And then to the east, 20 kilometers away is city E, which kind of looks like Brighton. So if in this thought experiment, if I knew in 30 minutes there was raining in city west, then this information would tell us that there is no rain in city east. Of course, if we have a regression model that we've given it only input, the output, if we were using mean squared error, says that it's raining both places with 15 millimeters per hour. And then in the classification setting, it'll say with probability 0.5, things are raining 30 millimeters per hour and this. And of course, you could also say to me, well, of course, the input is only the input of the previous time step, not what happened at 30 minutes. So there's no way the model could have used this information to tell us what happened in city east. Furthermore, you could also say, well, look at threat score or critical success index. This is CSI. A number of 0.5 at 15 millimeters per hour or 0.5 at 30 millimeters per hour is a really good metric value. What do I care that this model doesn't necessarily says that, rains in one city and not the other? But, very little time do we necessarily care about exact rain rate at some point in the future. We might want to poll our model about other questions that we care about. So one thing that we might ask is, what is the probability of rain in both cities simultaneously at 30 minutes? By construction, the truth is that's impossible. Rain either will end up here or end up there. But the regression model says that this happens with probability 0.1. And the classification model says this happens with probability 0.25, so 0.5 squared. And that is one downstream effect of an incorrect prediction due to a conditional independence assumption. I could ask a second question. What's the probability of no rain in city east over the next hour? So the truth is probability 0.5. And if I had a regression model that made a prediction every 5 minutes, it says that's probability 0 because there's always going to be rain. And the classification model, because it's independent both in time and space, it is 0.5 to the 8th, so like 40 minutes divided by 5, I guess, divided by every 5 minutes, so there's 8 frames. So again, incorrect prediction of the amount of rain for that probability of no rain over the next hour. And then what if I care about catastrophic flooding, or not catastrophic flooding, but a large amount of accumulated rain? So what's the probability of 20 millimeters of rain over the next hour? That's again 0.5, and then regression model says 0, and then the classification model says this. And so if you're issuing flood warnings, you really care about being able to pull your model for this and other questions and making sure that things are exactly correct. So this might give some amount of evidence that saying direct prediction by having this loss function may not be the correct thing to do. And here is a point I think that a lot of people in the community know, but I think it's worth bearing out again, especially with statistical systems, that the forecast quality, the scores on these particular metrics are strong, but the forecast value, the ability to make better decisions, depending on the type of question that we have, ends up being kind of poor. So kind of what went wrong here? The baseline models did this directly predict grid cell wise rain rate probabilities. And these are like some version of like discriminative models. So what our thought was, both at sort of the Met Office and DeepMind, is to think about this in terms of a generative model. So given the input, we want to have a realization of what would happen at the output. Here, kind of the model ends up in this little red box here, and kind of the big key of research is how to model this red box. And this gets to a generative model of radar. So our inspiration is to have a neural sampler. So very similar to like an ensemble NWP, so that given sort of our input, we're given n realizations of the output using some sampler. And then to go back to the desiderata that we want consistent predictions across spatial and temporal scales, the ability to capture rare event, and to be able to account for uncertainty. And because we have the sampler, we can calculate relevant probabilities, such as probabilities over accumulated rain over a catchment area from the realizations itself. But how do we construct this sampler? So one thing that has been done in the literature and has been pretty well developed since 2014 are generative adversarial networks. So probably a lot of you are familiar with this work, but if you're not, I'm going to give kind of like a one-slide overview. So to a first order, generative adversarial network is a sampler that generates deterministically given some noise. So this Z is drawn from like a normal distribution. This is fed into a neural network, and then out would spit out something from the data set that you trained on. So if you're ImageNet, you might have a lot of pictures of dogs. And so the input of this latent here, you feed that into a neural network, and this transforms this into a picture of a dog. Of course, we want more control than just sort of, random, I guess, like pictures of different rain. We want to know, we want to give it richer conditioning. So one way that we can make this a conditional network is to add more information. So one is you can add a categorical variable. So telling your neural network that you want to produce like a butterfly or a dog or something else. So you're feeding it a latent. So this accounts for uncertainty, and then you're giving it a categorical variable. So in this case, a butterfly, and then put it into a neural network, and out comes, a monarch butterfly here. And what makes a generative adversarial network is how it's trained. So unlike having a static loss function, which is both true for kind of what we were mentioning in sort of the baseline models and for sort of many other models too, is you have actually a second neural network that's used as part of the training. And so the second neural network tries to identify whether samples that it's given in its input either came from the generator itself or from a corpus of real data. So in this case, a corpus of dogs. And the generator will try to produce images that will fool the discriminator. So there's this back and forth game that happens through training, and the hope is at the end of training, the generator generates things that look a lot like the data distribution. So we have this generator, and what we're going to give to input are latents and kind of our past conditional frames. But what I've showed you are static images. So how do we do this in terms of large scale, high resolution images, and doing this for essentially what is like a video prediction problem? So we're gonna, I guess, use or build upon some work that DeepMind has done on images. So looking at this work, Big GAN, and then its extension to video. So this DVD GAN or dual video discriminator GAN. And this Big GAN is basically the conditional generative model that I showed you in the previous slide, which you're given some noise input and a categorical variable, and this spits out a high resolution image. And the DVD GAN gives you, given some noise input and video frames of input, a continuation of what might have happened in the video. So we're going to build upon some of this work. And this is kind of our generative model for radar. So our radar generator is here, and it's given context to your input frames and some latent variable. And then this will give you a realization of the output. And there's 3 losses here, so 2 discriminators, and then 1 extra regularization. So this temporal discriminator will either get inputs from a realization of our output or the actual observation itself. And this will ensure, and this is a 3D convolutional architecture that ensures spatiotemporal consistency of realizations. We have a second discriminator that looks at each frame individually to ensure that each frame is more spatially consistent, and this also helps stabilize training. But we also want to make sure that things are location accurate. So precipitation is in the correct place. And so we have this regularization, which looks at the mean of the predictions and compares them to what happened at the truth, weighted by some weighting of the output. So this may look a little bit weird in terms of regularization. Had we removed this weighting term and used a squared on the outside, this would be a squared energy distance. With the data that we have, sometimes we had some noisy pixels that had arbitrarily high rain rates, so training was a little less stable. So we use this as a bit of a compromise. We could have probably done other things that were a little more consistent, but yeah. So it's since this does not have no longer is like a proper score or a proper scoring rule, we call this a regularization, but it was inspired by energy distance. And so the generator architecture looks like this. So this would be given past context of 20 minutes, and then it would give you a realization of a nowcast over the next 90 minutes. And so on this observations here, this is what happened in the ground truth, and this is the prediction from the model. And the generator itself has a lot of architectural stuff to account for uncertainty, which is one of our desiderata. We have multiple spatial and temporal scales. So the spatial scales happen because at each of these D down blocks, this decreases the resolution by a factor of 2. And then the temporal consistency happens by feeding this into a recurrent unit, or known as a gated recurrent unit. And this happens at multiple different resolutions, and the input comes from not only the resolution that it had previously, but also from previous information. But of course, one of the things that we also want to do is highlight rare events and be able to predict those well. So what we did is we opted for a different training strategy in order to ensure that the model tried to learn from rare events. So both on training and validation, we did random sampling of crops, especially if we looked at particular verification scores like critical success index that looked at accuracy, that we only cared about things that happened point-wise. And then for training, we biased our sampling in order to have rainfall, or I guess like rainfall sequences or precipitation sequences that were biased toward higher rainfall. So 94% of the pixels in the UK data set have no rain. And we also did not want entire videos that had only no rain. That's not a really interesting prediction problem. So we biased our training set in order to have predictions on no rain. But when we did validation, we did it on the full training set, or the full validation set. And of course, we have a fully convolutional architecture. So this allows us to do evaluation when possible on the full radar image. And so this is what allows us to have these spatiotemporally consistent predictions, so this box in DGMR, even though that we train on much smaller crops. And so let's discuss sort of the quantitative verification and how this looks and compare this to kind of what we see in the predictions themselves. So if we look at critical success index, which is a very standard metric that you use to understand how well your model is doing in predicting precipitation, we have three deep learning models. So UNet, two versions of axial attention. So looking at the mode prediction or a sample prediction, and then deep generative model of radar. So we look at 20 predictions from the ensemble versions. And we also compare this to an ensemble physics-based model, PySteps. And I think what you see here is that sort of all the deep learning models to a first order perform sort of similarly, and they all do better than PySteps. But as I mentioned before, the UNet model and as I'll show sort of like the axial attention models do this, perhaps do this because they blur at longer and longer prediction intervals. And what CSI does not account for is blurring. And actually one of the ways in which you can game CSI is by blurring or hedging your predictions. So let's see what happens when we look at what is sort of the effective resolution of the nowcast. So one other standard metric is looking at the radially average power spectral density and looking at 30, 60, and 90 minutes. So this says nothing about location accuracy. It just says what are the spectral properties of the prediction themselves. So what we would ideally want is our observations are in this dashed black line here, and we want our predictions to have the same power over different wavelengths as this observed black line. And UNet, I think, is like an easy one to see, and you'll see that it loses power progressively over time. And this is also true with the axial attention model. And this loss of power over time is due to blurring. And then there's this tail component here, which is high frequency noise, which I'll show in the next set of slides. And one thing that we can do is, well, given the amount of blurring that there is, one question we can ask ourselves is, to what extent is this actually giving you a high resolution nowcast? So things that are actually 1 kilometer by 1 kilometer resolution, or is it something that blurs so much that the effective resolution is much smaller? So one thing that we did was we compared this to taking the observations themselves and then upscaling that observation or downsampling that observation from 1 kilometer by 1 kilometer resolution to 16 by 16 or 32 by 32 kilometers. And then you can see sort of the power spectral density here. So you can see there's a match at 90 minutes with the 32 by 32 observation. So what does this mean? So this means that as time goes on, nowcasts are progressively blurrier and blurrier, and then the effective resolution of the nowcasts become far less than the nominal 1 kilometer. So at 30 minutes, they have the same spectral properties as 8 kilometer by 8 kilometer observations, but at 90 minutes, it goes up to 32 by 32 or 16 by 16 observations. And if you look at sort of the physics-inspired models, PySteps, those are very close to the observations. And our generative model also does sort of similarly strongly. And then if you look at a probabilistic verification, look at continuous ranked probability scores, CRPS, we can look at this both at a pixel-wise level, so this is our pooling scale 1, but then also look at what happens when we average over larger areas to see to what extent things are consistent if you're doing accumulations over larger catchment areas. So if you cared about accumulation of rain over a wider region for, say, flood prediction. So at 1 kilometer, as we sort of belabored this point, since the output is per pixel, all the deep learning models, except for UNet, which is deterministic, performs similarly well. But if you increase the amount of aggregation, so this is 4 by 4 kilometers and 16 by 16 kilometers, you can see that the other sort of baseline data-driven approaches actually are worse, given that they give you inconsistent predictions, whereas the physics-based PySteps and DGMR are similarly strong across scales. So this tells you a lot about forecast quality, but like, what does this mean in terms of nowcasts? So we had an intercomparison case study. So the chief operational forecaster at the Met Office, who was independent of the team, gave us an example which he thought was difficult and something that he would like to see if one of these models performed particularly well, because this is a particularly important case. So there are these convective cells here, which are in this like light blue / red, which are typically important because they, give you this very high precipitation, but are also very difficult to predict. And if we look at a traditional nowcasting system, so this is one realization from PySteps, you can see that there are convective cells, but they're kind of in the wrong location. And then you can see at 90 minutes, it's missing this low to medium precipitation in this area. If you look at UNet, it kind of gets the broad strokes right, but because of blurring, it misses all this small scale structure that is this important structure. And then if you look at an axial attention sort of like mode prediction or pointwise probabilistic output, you can see sort of the similar blurring and missing the small scale structure. And I think what is interesting is that these data-driven models, even for this use case, are better than the PySteps approach. And then DGMR had, at least at 60 minutes and to some extent at 90 minutes, starts to preserve these convective cells. What is interesting about this in terms of automatic metrics is all the neural network models kind of perform similarly on CSI at various thresholds and CRPS, but you can see qualitatively this is very, very different. And then when we asked expert forecasters in a blind study which they would prefer, and the preference was based on, given they knew what happened with the ground truth and then looked at PySteps, DGMR, and axial attention, they found that our model was the best. But actually, this is not the point that's really interesting. I think the point that is interesting is that this physics-based model, that even though is not doing so well in automatic metrics, is actually what preferred sort of 2.5 times to axial attention. So this is a first choice ranking, but if you look at a pairwise preference, PySteps typically is preferred by operational forecasters 2 to 3 to 1, between 2 to 1 and 3 to 1 over, a data-driven approach. And so what happened here in terms of the disparity between what downstream users would want and what happened with the metrics? Well, I think it's a limitation of quantitative verification, but I don't think it was. I think it's basically that we're using the verification for models that it was not designed for. So the weather verification community has done really amazing work. I think the machine learning community can take a page from them and really look at and probe our models in a very much the same way. But a lot of those verification metrics were exclusively used for NWPs or other physics-based systems. This was not necessarily intended to also be used for statistical systems. And so it might be that our judgment about forecast quality and forecast value is more tenuous now than it has been in the past, when everything was some version of a physics-inspired model. So one thing that we did in order to try to have a more direct comparison of would this be useful for downstream users is performing an expert evaluation. So we performed an experimental psychology experiment for operational meteorology, and we did a controlled study of expert judgments for the assessment of sort of ML models. And we worked with the chief operational forecaster to design the study and adjust the type of assessments made. So there were 56 meteorologists that were participating in the study that weren't part of the paper, and we're hugely indebted to them. And they were the ones that told us whether or not they cared about this model and which model they cared about. So they did not come from ML background or a background that cared whether or not a deep learning model was good or bad. And they would tell us if things were wrong. And so I really liked having sort of an independent third party look at this in terms of being able to tell us if we did well, and maybe more importantly, what things we did wrong, and how can that inform our decisions in terms of new ML approaches. So we did this protocol in 2 phases. So we had a browser-based preference ranking depicting sort of real images and our predictions. And then in phase 2, we took a fifth of the people that were in the study and then did a retrospective I guess, interview with them. And then obviously due to like current circumstances, the protocol has happened completely remotely via a browser-based form. And this is kind of what the form looked like. So they were given the input radar field and what in particular that they were looking at, and then the observations of what actually happened, and 3 predictions over 30, 60, 90 minutes. And these were anonymized and randomized order. And then we asked them to do a first choice ranking. We had a design decision to limit this to this information. In an operational setting, meteorologist will have other information, but we wanted to limit the number of confounding variables, so we left it to this. And our case study was with each person looked at a total of 23 cases from a corpus of about 1,200 cases. So 10 of them from each person were looked at precipitation above 5 millimeters per hour, and 10 at above 3, and then sort of 3 special cases, one which I outlined earlier in the talk, and then 2 other ones that were identified as sort of unusual weather and sort of difficult, interesting events. And then in phase 2, we did a retrospective interview where during we used Hoffman's protocols for cognitive analysis. Meg Fitzsimmons, who was at the Met Office, ran this interview and did a really amazing work in terms of human evaluation. This happened in 3 steps. So a recall of task and rankings. Sweep 2 did a detailed emotive reasoning behind decisions, and Sweep 3 looked at sort of blanks and mistakes in our picture in the decision-making process. And of course, like, there are certain design decisions that obviously will make results a particular way. So question phrasing was obviously very important. So what we wanted to do is try to make a judgment of sort of accuracy and value. So what we decided to use in terms of a phrase is asking a preference based on opinion of accuracy and value. I mentioned this point about additional information that in an operational setting, a meteorologist would have, but we limited this for this particular study. And then we also wanted to make sure that people were professional meteorologists that were qualified for 6 months. And then things were anonymized to make sure that their performance on this did not have any bearing on what they did day to day, which is issue guidance for various industries. So these are the results for both 5 and 10 millimeters per hour, and our model does pretty well in both of these cases. Again, I would like to point out that even in this larger study, there is compared to a certain type of data-driven approach, physics-based models were vastly preferred over a certain type of model. And so we want to make, I guess, like very clear that this is maybe a first step, but something that is a bit curious. And if we are using our models for this type of operational setting, maybe some of the tools that we want in terms of metrics should be more aligned with this. And kind of what would the desiderata for something like this look like? So I kind of pulled some transcript extracts to see what various meteorologists wanted from models that they would want to use. And so this one did not particularly mind if the intensities were underdone, as long as the spatial variation looked realistic. This person wanted something that's slightly realistic. Doesn't have to necessarily be location accurate, because they have a lot of background experience, and so they could put their own knowledge of physics into it. That's not to say this is true for everyone. So even lower resolution or unrealistic ones can be useful, but you have to make sure to get the broad shape correct. And then tracking movement is probably quite useful. I'm going to skip over this last quote bit due to time. It's just saying nice things about our model, and that's not that interesting. And I think this is maybe a step 1 in terms of how we should think about this going forward, which is thinking about operational driven design and having more close feedback with people that might be end users for this particular product. Obviously, if we're doing things to tackle global challenges, there might be ways in which our predictions might score well, but aren't actually useful. So we should make sure that we have both an assessment of the insight of how well our models are doing and having that feedback in order to improve our models going forward. And sort of as kind of conclusion, obviously like nowcasting fills in a gap of NWPs where in the first couple of hours it doesn't perform well. And it kind of fills in a gap where physics based simulation is not that great. And I think this shows some promising results on how deep generative models might be used for nowcasting. I kind of, some things that I think could be improved on are still high intensity events and ones around, and then better understanding of how well these models do in terms of convective initiation. So I think this is only step one. I think hopefully people in the audience will think about these problems and make these systems even better. And we want to make sure that some of these tools do provide better decision-making value by real-world experts. And of course, like we're all here because this is of interest to many sectors in the public. So I wanted to leave with sort of two thoughts. So if you wanted to take a look at sort of the model and play around with some data at a collab, we have a GitHub repo that has a collab of some of the data, including the data that we can train on. So hopefully like you can use this, build upon it, maybe try something completely different and better, and that would be great too. And then finally, I want to leave with a parting thought, which was one of the initial thoughts, which are sort of all models are wrong, but some are useful. Maybe for something like this is, all forecasts are wrong, but some are useful. And maybe we should think about how to do better measurement of data-driven approaches in order to really understand the second clause, to understand the utility. So yeah, thank you very much for this. And there might be some Q&A, but it's very hard for me to switch between slides and something else. So apologies in advance if I missed some stuff that happened during the talk earlier.
No, that's perfect. Suman, thank you very much for a really fantastic talk. That was great. I'll start actually with a comment from the chat first. Thanks for the great webinar. This is not only a great presentation, but also a great basic course in ML. And so I think it was really nice to have this nice introduction between basic ML and the application. So it was really, really, really fascinating. There's quite a few questions already in the chat and in the Q&A, and people can still add more to them. I'll kick off maybe with the first one. I'll read them out for you, Suman. You can relax if you need to read it. The first one is by Thanos Ninas, who's a great talk. And so it's quite a technical question, so you might have to think about it. In the graphical representation example provided, selecting one or the other branch of your graph means in a way that information flows from one or the other direction, which is in a way similar to the upwind advection numerical methods, which is also has an information for if you go upwind or downwind in the standard advection scheme. So Thanos asks, and the standard advection scheme is really also this upwind scheme is very diffusive. So Thanos asks, are there parallels to be drawn between this information flow from one or the other direction in the numerical methods and in the ML methods?
So the short answer is, I don't know, but you're also not the first person that asked me about this. So the last time someone asked me about this, I said, no, there can't be any connection. This is really just like a statistical issue that has to do with, some amount of uncertainty. And the person that I talked to said, no, I'm more convinced that, these things are a parallel. I don't want to say anything more because I have not thought about this rigorously enough to make any claims, especially on something that there is a recording. But I have a feeling you are not the first person that says it. I think there is a parallel. It's just that I have not looked at it that closely. So that it would be like a nice thing to, at least for me to think about more closely. And maybe now that it's, past the holidays, this is something that I will think about.
No, perfect. Yeah, it certainly wasn't an easy question to pick up. So how does there's a question from David Ehrman, and who asked, how does the model deal with centennial, millennial events like extreme flooding events or so that are basically out of training? And what are your thoughts?
Yeah. So, I mean, I guess it kind of depends on the type of events that there are. So, I mean, like, one thing that deep learning models are not so great at is really being able, they are very large, very flexible models, so it's very hard to reason about what might happen out of distribution. So for certain types of events that happened in mid-2021, the short answer is like we would have to try and see, especially with the data itself, if the prediction is something like there's a large event that moves in some direction but then gets stuck for a very long period of time and then there's flooding, I'm more optimistic about this than if there are other weather related phenomenon where something happens with a convective initiation de novo, and this happens very quickly. The only other thing I can add to this was there was like the Stonehaven flooding event that happened a couple of years ago. And I did look at our model for this event, and it did a pretty good job of a prediction like that. But this would be sort of a case-by-case basis. I would like to see how this looks on different types of events. One of the things that makes this a little bit difficult in a prediction scheme is that you need to have a large enough corpus of radar data, and radar data that's that you would give before the flooding event itself to see to what extent it would be useful. So, there are other models that train, like 3 days on and then validate on a couple days off, and that's sort of more in-sample distribution. I'm not necessarily convinced that this might give you an overly rosy view of the prediction itself. But I think it depends. It's a little bit better than I thought it would be, but as these cases don't happen that often. And that would be a thing that would keep me up at night, is like, is this thing going to miss something that is catastrophic? But for me, I guess the way I would think about this is how to do this. How would I think about doing this type of thing with distribution shift, and how to measure this force before maybe tackling this in the model itself kind of blindly. But that is a great question.
Great. There's a question, a general question, and that's more about why would you conclude that the generative models are spatially consistent, as you said earlier on in that talk?
Oh yeah, so I think maybe the question is that I might have said because the CRPS scores look very similar across, I guess like pooled over space metrics, that this is true. So I guess doing well on CRPS across different scales does not imply spatially coherent predictions, but I think in the generator slide there was a box around DGMR. That's a prediction from the model, and that looks relatively spatially coherent to me, or at least compared to some of the other ones. So I should have been a little more specific about that. So when we look at the predictions themselves, or when we give them to meteorologists or other people at the Met Office, they're the ones that tell us that it's sufficiently spatially and temporally coherent. But again, this is something that like having better measurement of spatial and temporal coherence would be actually useful, not only actually for this this line of work, but actually in like ML in general. So that is a very good question, and I'm glad that hopefully that like sorted out maybe some misunderstanding that I may have generated by implying, CRPS implied spatial consistency, or radially average PSD.
Great. I might sneak, or Duncan, you were just coming in or no?
Yeah. I had a question just following up on that. You mentioned the meteorologists, and you did this fantastic job of evaluating how they felt each model performed against the observations, and went into a lot of detail in that in the paper as well, which was great. I'm curious a little bit about how much the meteorologists are kind of in the loop for nowcasting forecasts, because presumably you want to get the forecast out pretty quickly, and so perhaps in some settings they're not. And I also wonder to what degree there's a lot of interest in ML obviously, and particularly climate applications in explainable or interpretable AI. And I wonder how much they were kind of put off to some extent by the pretty large complex model that you had to invoke in order to get such skillful predictions, and how that plays into this.
Yeah, so for the second question, I was really worried about explainability too. I think kind of surprisingly, the meteorologists did not mind it as much, because I think like the predictions were relatively good. Obviously, in an operational setting, this is not the only thing that they would rely on. They would rely on other things. And so maybe I think between that, if you think of this as a tool, maybe not a tool with the amount of explainability that all of us would want and something that we should still work toward, this could be still something that is useful. And then the first question, sorry, I've now forgotten it.
Was, oh yeah, well, I was wondering, how much the meteorologists are actually in the loop in nowcasting, and that.
Oh yeah. Yeah, so I was curious about this too. There was a workshop at the Met Office in nowcasting maybe a couple years ago now, and they said sort of the minimum lead time that they would need is 60 minutes in order to. So that was much faster than I thought. Obviously, like the longer you push it out, the better. But the absolute minimum is an hour. I think if things are really catastrophic, then probably an hour is not good enough. So weather prediction over 90 minutes to 2 hours is still, again, not that long. We want to get this out further. There are papers that are starting to do this, and I think it's sort of the obvious next step. And then I guess going back to, issues of climate, I guess like with climate, my feeling is explainability, or just a broader based understanding of why models are making predictions are going to be much more important in that setting, because we won't have ground truth. We can't wait 50 to 200 years to see if some model actually predicted what was going to happen. And even if it did, how would we know? So I think this is like, when I think about that, there's kind of two minds, which is like, one, which is, yes, there should be a better marriage of physics style thinking with statistical thinking. But the other part of me says, maybe we want to keep really flexible models, but our measurement needs to be a lot better. And then obviously people in the audience may have very, very different viewpoints. And I think like having different philosophies of how this should be done and different approaches is good. I don't think everyone should think like me or like anyone else. I think it's like a pretty new area. So yeah, it's this unanswered question, but it's like a really interesting one.
Great, thank you.
I mean, effectively, you answered also another question in the webinar, exactly that there are these two types of approaches, the more physics-based driven and the statistical, and how could they be combined in the future? I guess it's a big question to use the strength of both of these.
Yeah, so yeah, you go into these, or like there's these three major conferences in machine learning, like ICLEAR, NeurIPS, and ICML. And the workshop section is sort of at the end of it. And it kind of is like new cutting edge research of things that people want. And everyone calls this grand challenge of like marrying physics with machine learning. So this is not, this is kind of the, I don't know how many X pound or X euro question this is. This is like the big grand challenge. And I think it's like a really interesting intellectual one that I'm only starting to get into, but it's just, I don't know, like it's fascinating.
Yeah, I mean, the same question came from me also up in your talk when you said the GAN style approach is sort of a video prediction task, which also again misses then the input of some of the knowledge, physical knowledge that you could add to it. It's the question how you add it, I guess. That's a real challenge.
Yeah, so I mean, the reason why we just thought of this as a video prediction problem was, I guess, one is, we had these models in-house. We have a lot of experience with it experimentally. So applying it to this and making the tweaks where we wanted to, be on solid footing. I guess the second part is the data itself is, we don't have full atmospheric state information, right? So we have partial observations. And so, in my very naive understanding of, fluid dynamics, you kind of need a much fuller state than what we currently have. And so it was hard for me to think about how to marry those things given the data set. You have a different problem, you have different data, then the approach might be much more amenable to having more physics style thinking. But this was, we went purely data driven because we felt that A, that was kind of what the data gave us, and then B, what we were most comfortable with in our sort of first pass and sort of our first foray of like learning about these type of predictions.
Yeah, and you nicely pointed out in the introduction is that the traditional methods or the traditional images you try to predict tend to be quite a bit smaller than some of your input data here. And when you think of it, I mean, the radar data, for example, itself that you have also has another dimension in terms of other radar signatures you could pull out, but that would make it just an even bigger problem, I guess, in terms of the data amount for the input side.
Yeah, I mean, when we first got the data, we were like, oh my God, this is enormous. So we had like a little bit of shock before we had to think about how to do this. But you know what, like, this is the challenge that me as a researcher like needs to solve. Not that we should change the data to remove some parts that might be useful, right? Like, there's a lot of really interesting structure with radar and other type of data, and I think a lot, Andrew Ng is a very strong proponent of the particular problem area driving research, and the research also driving the application area, and that being a virtuous cycle. So you can think of these type of problems as being able to drive research and driving it in really important ways. So we shouldn't necessarily be scared because the data doesn't look like things that we've had before. This should, make us, I don't know, do my job as a researcher and think about how to do better prediction given this new and very structured data.
No, I think that's exciting that climate and weather can also push ML forward as well. I think that's
and I mean, if you look at like deep learning historically, that was pushed a lot by computer vision data sets, and to like a lesser extent like speech recognition. Like, those were the problems at hand that were hard, and that's what people would tune to because those were hard problems. So this is a new hard problem, and one that arguably is more important than these other things. And hopefully this will, drive research in ML in really interesting ways. I'm optimistic about it. But yeah, it's just a matter of getting the data and then getting people excited, and then obviously like getting people together with different experience and background.
Yeah.
That's almost the perfect philosophical way to end the discussion. That was really great. As you said, we have lots of data in climate, and we have lots of questions and problems. So there's lots of work remains to be done. So thanks a lot again, Suman, for a really, really great talk. I should point out to people that we're not done yet. There's more seminars to come. And actually the next seminar next week on 12th of January will be Martin Schulz from Forschungszentrum from Jülich Supercomputing Center now, and together with actually Duncan. And the title will be How Can AI Improve Weather and Climate Prediction? So I hope you can all join us again. And thanks again, Suman, for a fantastic talk.
And with that, I'd like to once again thank everyone involved. So our speaker, Suman Ravuri, thank you very much. Our host, Philip and Duncan, our sponsors and co-conveners, Switzerland, and I hope to see you soon.